Now that we've looked at the different types of linear factors that we could have in the denominator, we're going to start expanding that to quadratic factors. But a couple general rules need to be held. Okay, so the first one is that every irreducible factor must be included. Okay, so if you can't factor the factor any further, you have to include it in the denominator of one of the other fractions. Okay, and the other rule is that every possible power of those factors must be included. So if you have a irreducible factor raised to, say, a third power, then you have to include the first, second, and third powers as different denominators. Okay, so every possible power. So every irreducible factor and every possible power. Okay, and the other thing, which I didn't actually write up here, but is also true, is that the numerator must be of lesser degree, specifically one lesser degree, than the irreducible factor. Okay, so in fact, I'll mention this up here. So the numerator must be of one less degree than the denominator. And that is, again, to make sure that the fraction is a proper fraction. Okay, so using those three rules, I'm going to try to solve this, or decompose this into its partial fractions. Okay, I've got x squared plus x plus 2 all over the quantity x squared plus 2 times the quantity x squared plus 1 squared. Okay, now I got to get rid of this to make some space. So again, these two rules help me to get the denominators. All right, so the denominators are going to be, now another thing to notice is that x squared plus 2 is irreducible. I can't factor x squared plus 2. Same with x squared plus 1. If x squared plus 1, if that was x squared minus 1, I could factor it into conjugates, but it's not. It's a sum of squares, which is prime. This isn't even a sum of squares, it's just two terms that we can't factor out. And so these are both irreducible quadratic factors. All right, and so the denominators are going to be, the first one anyway, is going to be x squared plus 2. That one has to be included. But the power is 1, so I only need a 1 power there. The second factor is x squared plus 1. So that has to be included, but also every possible power. So because this has a square on it, I need to square, I need a second denominator for that one with a square on the bottom, or with a square as the exponent. So I get x squared plus 1 squared. So this gives me three different fractions then. Okay. The other thing that makes this difficult is that the numerators, like I said, all have to be 1 degree less. Well, that means than the irreducible factor. And so since these are each quadratic irreducible factors, the numerators all have to be linear, degree 1. So I'm going to write those with variable coefficients. I would call them ax plus b, right? That's a linear factor. And then cx plus d, I can't repeat my variables, so I need distinct letters up here. And ex plus f. I just go right down the alphabet. A, B, C, D, E, F, G, H, I, J, da, 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 da. Okay. So then, just like we've done before, we multiply both sides by the LCD. When you do that, and I'll write it up here, but just to give you a hint here, might simplify things. If I were to multiply this first side by x squared, the left side by x squared plus 2, and x squared plus 1 squared, so that's the LCD, everything cancels off, right? And so generally speaking, and you could apply this to every one of these problems, the left side is just going to be that numerator. It is x squared plus x plus 2, all right? after you've canceled everything off. The right side, if I were to multiply the first term by this LCD, which would be multiplying by x squared plus 2 and x squared plus 1 squared, what will happen is that the factor that's present will cancel off, right? But the missing factors will multiply the numerator. And that's actually going to be a general rule also going all the way down. So instead of writing this out and canceling every time, I'm just going to apply that rule. Basically that the denominator cancels and you're just going to multiply the numerator by whatever is missing, all the missing factors. So if I look at this denominator on the left and I figure out what's missing, which is the x squared plus 1 squared, then I multiply the numerator by that. So ax plus b times the quantity x squared plus 1 squared. Okay, that'll work, which makes sense. That's what we would have there. And again, I'll repeat that on the other two without having to write out the LCD and do the canceling. So it's going to be the numerator, which is cx plus d, times the missing factors. Well, this has an x squared plus 1. It's missing an x squared plus 2 and another x squared plus 1 to get the square. So it's going to be an x squared plus 2 and an x squared plus 1. Okay, multiplying that one. Then the ex plus f is missing, well, it has the x squared plus 1 squared, so it's missing the x squared plus 2. Alright? And that gives me all of the factors that are left over after doing the canceling. Okay? So now, this looks horrible. It's long and I have to expand the entire right side. Okay? Again, we expand the right side and then match up our degree terms, like our square terms, and just equate the coefficients. Okay? So that's how we're going to set up our system. So on the right side, this is incredibly long, but we'll go for it. I need some space, so I'm going to move my equal sign over. I'm not even going to write the left side, and I'm going to expand this. Now, I like to save the variables a, b, c, d, e, f to the end and expand the other polynomials first. Just makes more sense in my head. I can do it quicker. Here, x squared plus 1 all squared is a perfect square trinomial. Square the first term, double the product, square the last term. Okay. Over here, I have the cx plus d times, now if I distribute this, x squared times x squared is x to the 4th. If I do x squared times 1 and 2 times x squared, that's 1x squared and 2x squared makes 3x squared. You add the constants there to make 3x squared. And then 2 times 1 is 2. So I'm doing basically the FOIL method, but I'm skipping that middle step and just combining the two terms in the middle right away. And then down here on the end, I've got ex times x squared, which is ex cubed. Ex times 2 is 2ex. F times x squared is fx squared. And f times 2 is 2f. Okay, well, I'm not done. I still have to expand these other polynomials, which is, again, quite long. I have to make sure every term on the left multiplies every term on the right in these parentheses. So it's going to be ax times x to the 4th. And I'm going to go through this kind of fast rather than speaking out each step. So ax to the 5th plus 2ax cubed plus ax. That's ax times all three terms. Then I do b times all three terms. It's going to be bx to the 4th plus 2bx squared plus b. Then I'm going to do cx times all three of these terms, which is cx to the 5th plus 3cx cubed plus 2cx, and then I'm going to do d times all three terms. Now I'm getting pretty far down the line. Let's maybe run this back here, jump another line. So that's, what's that? It is dx to the 4th plus 3dx squared plus 2d, and then I still have these four terms hanging out on the end. So that's ex cubed, 2ex, fx squared, and 2f. Okay, so that gives me all of my terms. Now none of these are like terms really. If you include the a, b, c, d, e, f as variables, I can't combine anything here. So what I'm going to do instead is I'm going to group these together by degree. fact, I'm going to make a little table. And the degrees that I see are basically everything less than 5. I see 5, 4, 3, 2, 1, 0. They all have, they're all present. So I'm going to write those down. 5, 4, 3, 2, 1, and 0. Those are my degrees going down in a column. So what I'm going to do is I'm going to match up the coefficients of each of those degrees. Okay? So for degree 5 on the left side here, I have no degree 5 terms, so I'm going to call that 0. All right, 0x to the 5th. On the right side, I just add up all of the coefficients of the degree 5 terms. That's a plus c. Those are the only 2 degree 5 terms. Degree 4 terms, well, there's none on the left. Let's see, on the right for degree 4, I have a b and a plus d. And that's it, okay? On the degree 3, again, I have a 0 on the left. There's no degree 3. But on the right side, I have a 2a. I have a 3c. And I have an e. All right. The degree 2 terms, I have, let's see, where am I degree 2? Oh, up here I have a 1, right? I have 1x squared on the left. Then on the right, x squares, I have a 2b. I have a 3d. And I have an f. Okay. And then my first degree or 1 degree terms, well, there's a 1 up here, 1x, right? Coefficient is 1. And down here I have an a. I have a 2c. And I have a 2e. Yep, that works. And then for my 0 degree terms, or my constants, I have a 2 equals constant, a b, I have a 2d, and I have a 2f hanging out there on the end, okay? Now this looks horrible, right? It's technically a system of 6 equations with 6 variables, right? It's got a, b, c, d, e, f. It's got, obviously there's 6 equations there, 1 for each degree, 0 to 5. And so sometimes you would say, well, let's just go right to the calculator, plug it in our matrix, and solve, right? And you could do that. You could create, because it's a 6 variable or 6 equation system, you could do a matrix with 6 rows and 7 columns, and you could plug in your first equation here would be 1, 0 for b, 1 for c, 0, 0, 0 for d, e, f, and then a 0 for the constant. And you could do that row by row, right? You could do, this would be 0 for a, 1 for b, 0 for c, 1 for d, 0 for e and f, and then the 0 on the constant as well, and so forth. You could do that. Lots of 1s and 0s, a couple 2s and 3s. I wouldn't personally. That'd probably take me just as long as solving this by hand. And the reason I can solve this by hand quickly is because if you look at the odd degree powers, just something I'm recognizing, the odd degree 5, 3, and 1 all have AC, ACE, ACE. They only have AC and E. That's 3 equations that only have 3 variables, which is solvable, right? If you look at the even degree equations, they only have B, D, and F, okay? And so what I would do is split this into 2 systems, each with 3 equations and 3 variables, and I would solve it by hand using the addition or elimination method, okay? Now what I'm going to do, I need to make some space. I'm going to erase all this work. I hate to do that because if I need it, it's a lot to redo, but I shouldn't need it, okay? As long as I keep my system here. So I'm going to get rid of all of this. All that's really useful for is setting up the system, or in this case systems. And so I'm going to take these aside. I'm going to take the 5, 3, and 1 and set those aside and work with those. So 0 equals a plus c, 0 equals 2a plus 3c plus e, and 1 equals a plus 2c plus 2e. Alright, those are my 5, 3, and 1 degree equations. Then I solve the system. Well, to solve this, I already have a and c by themselves, so what I'm going to do is eliminate the e from these bottom two equations and give myself another equation with just a and c and solve that. To do that, I'm going to take this middle equation, I'm going to multiply by a -2 so that I can get coefficient opposite of the e. So I'm going to have 0 equals, multiplying the -2 to every term, -4a minus 6c minus 2e. And then I bring this one over, it's 1 equals a plus 2c plus 2e. Add those together, the two e's drop off. Very nice. Alright, and then the a's, I get -4, oh actually let's go with the constants. I get 0 plus 1 is 1. -4 plus 1 is -3a. -6 and 2 is -4c. Okay. Then I'm actually going to take, so now I have an a and a c, here I have an a and a c. So to eliminate a variable, let's say I want to eliminate a, I'm going to take this top equation, move it down, and in doing so I'm going to multiply it by a 3. That way my a coefficients are opposites. So that'll give me 0 equals 3a plus 3c. Alright? And then I'm going to add those equations together. The a's will drop off. I get 1 equals -c. Well, that works out nicely because if I divide out the -1, that tells me that c is equal to a -1. I divide -1 on both sides. So I get a c value of -1. I'm going to store that over here. Let's do a equals b equals c equals d equals e and f. I'm going to store them so that if I need to erase some work to make room, I can do that. So c is -1. Hopefully you guys can just fill up a sheet of paper, right? These problems are going to probably take a full sheet or 2 per problem. They're not short, okay? And I would plan some time to do this homework. But I've got limited space, so I'm going to be erasing as I go. C is -1. Now, if C is -1, I can put that back into any of the 3 equations, but I like the top one because I can immediately solve for A. So I go 0 equals A plus, -1, right? It's the C value. And of course I add the 1 to both sides, and that gives me an A value of 1. So I know that C is -1, and A is equal to 1. Okay. Then I have both A and C, and I can use them in either of these 2 equations. I'm going to go to the bottom one and solve for E. It won't matter, I'll get the same E value in either of those equations. So if I go to the bottom one, I get 1 equals, now the A is really 1, 2 times C is really 2 times -1 plus 2E. And I can solve that equation for E pretty quickly. In fact, I get, actually let's just subtract the 1's right away. 0 equals -2 plus 2E. I'll add the 2 to both sides. That'll be 2 equals 2E, and of course if I divide out the 2, E is also equal to 1. That works out nicely. I've got lots of 1's and -1's up there, right? 1, -1, and 1 for A, C, and E. Okay? So then, so I've taken care of those 3. Now what I'm going to do is I'm going to go back and pull out the even degree equations and find BDF in a similar way. Of course, I need to erase all my work on the A, C, and E just to make some space. So I'm going to pull those, the evens, 4, 2, and 0. So I get 0 equals B plus D, 1 equals 2B plus 3D plus F, and 0 equals, no, not 0, 2. I gotta go with, 2 equals B plus 2D plus 2F. Did I copy anything wrong? 0 BD, 1, 2, 3, 1, 2, 1, 2, 2. Yeah, okay, I got it, right? And then I'm going to solve this. Similar process. I'm going to eliminate the F's and then use the resulting BD equation along with the first equation to get rid of, probably D, but I don't know, maybe it'll be D. Anyway, to get opposite coefficients, I'm going to multiply this second equation by -2. That'll give me -2 equals -4b minus 6d minus 2f. This equation, I just bring it across. 2 equals b plus 2d plus 2f. Now the f's drop out nicely. Actually, the constants over here drop off nicely. And I'm left with -3b minus 4d. Now again, I'm going to get one of those coefficients to drop off, one of the variables to drop off, so I need opposite coefficients. I'll use the b, so I'll take the first equation again and multiply it by 3 to get my b coefficients opposite. That would be 0 equals 3b plus 3d, again distributing the 3 to every term. And when I add those two equations together, the b's drop out. I get 0 equals, what's that, -d. And if I divide both sides by -1, d is just equal, d is just equal to 0. Okay, so that's nice. I put a 0 up here for d. Now I can use that 0, plug it back in to get b. So I use 0 equals b plus 0, right? And of course the 0 is unneeded, so b is equal to 0. So I can put a 0 up there for b. And finally for f, I take the two zeros, I plug them into either of these equations. I'll go to the top one because the coefficient on f is already 1. So I'll go, I should say the middle equation. 1 equals 2 times 0 plus 3 times 0 plus f. Well, the two 0 terms 0 out, disappear, and I'm left with f equals 1. So let's store that. And now I've solved for all 6 variables. I have either 1, 0, or -1. Okay, works out nicely. And so what I'm going to do now is I'm going to reconstruct my final answer. Final answer should always be the partial fraction decomposition, the decomposed fractions. Okay, so what I'm going to do then is get rid of some of this work and just write out my final answer, which is just the A, B, C, D, E, F plugged back in. So I get, what's this, 1x plus 0. Alright, so it's just x on top over x squared plus 2. And over here, cx plus d, well that's -x plus 0. Well, instead of -x, I'll just write a minus x, and the plus 0 I don't need, over x squared plus 1. Right, so just to refresh, this is 1x plus 0. This is minus x plus 0, which I have there. And then the e and f are both 1s, so that's an x plus 1 over x squared plus 1 squared. Okay. And there we have it. That is my decomposed fraction, the original rational expression decomposes into these three smaller rational expressions, each with an irreducible quadratic denominator. One of them has a power of 2, but all of those factors are irreducible. Okay, and then again, the numerators all have degree 1 less than the original irreducible factors from the bottom.